We now state the Lenz's law. So we had seen that the Faraday's law talked about induced current or induced EMF. Now Lenz's law states that this induced current is in the direction that creates, so the direction of the current is such that it creates a magnetic field by itself, and this magnetic field is such that it opposes the change in magnetic flux that produced it. Now this is quite a mouthful and we need to understand it properly what Lenz's law essentially means. So let us see it via examples. So let us see the first case. So we had already talked about this setup before. So this white is a metal conductor, or you have these two parallel plates or parallel bars, and then you have a conductor which is moving rightwards with the velocity v, and you have the magnetic field going into the screen. So the magnetic field is like this. This is going into the screen and it is perpendicular to the plane of the loop here. So then we say that the current is flowing in this particular direction given by the red arrows. So the current is flowing in this direction. So we have indicated the direction with the red arrows. So why is the current is flowing in this direction? So Lenz's law tells us the direction of the current. So let us see the corresponding loop. So we take this plane and we just put this plane as a loop like this right here. So this is the loop like this. So if the current is flowing like this, so say this south side is into the screen and this north side is out of the screen. So this is out of the screen. So when the current flows like this, it creates a magnetic field which flows out of the screen. So this magnetic field is flowing out of the screen. So again, when we are moving this rust colored bar towards the right with velocity v, what is happening is we are getting more and more magnetic flux going into the screen. So as you move this bar towards the right, you get more and more of the magnetic flux here into the screen. So Lenz's law states that the current will flow in a direction so as to oppose this change in magnetic flux. So what will the current do? The current will flow like this, as in this figure here. So this is the direction of the current flow. So the current will flow like this. This flow of current will produce a magnetic flux out of the screen. So this flux which we have produced out of the screen will try to cancel the flux going into the screen, because the basic scenario right now is that this as bar moves towards the right, so the flux into screen increases. Flux into screen increases. So the Lenz's law states that we are going to produce current, and this current will have its own magnetic field which will oppose this increasing flux. So the current flows, so it produces flux in opposite direction. So if it produces flux in the opposite direction, it is trying to oppose the increase in flux into the screen. So this opposition is done by producing another flux which is out of the screen. So this is flux out of the screen. Now consider example 2. Now the bar is moving towards the left with velocity v, so the flux is decreasing. So the flux is decreasing. So Lenz's law will produce magnetic field which will increase this flux downwards. So this is into the screen. So therefore the current, as you can see, now the current will flow in this direction. So the current is flowing now in this direction as in the loop here. So when the current flows like this, the magnetic field is produced in the direction downward. So you can see the magnetic field is now being produced downwards. So again, the Lenz's law basically says that the current is produced so that the current itself can create a magnetic field which opposes the change in magnetic flux that produced it. Now consider force acting on a loop. Now as this bar moves, this bar is moving towards the right. So this bar is moving towards the right. It experiences a force. So the magnetic force is given as I L vector cross product with B vector. This we had discussed in previous chapters. So the magnitude of the force would be I L B sine theta. Now B is into the screen. So this B is cross, this is into the screen. And L vector is nothing but this length. So the angle between L and B is theta is pi by 2. So sine theta is 1. So sine theta is 1, and this is what we will put in here. So you get ILB. So since bar is moving with constant velocity, so this bar is moving with constant velocity. So the force FB vector, this force acts in the opposite direction of the velocity. So this force will always try to reduce the motion of the bar, because by Lenz's law it is trying to produce a magnetic field which is opposite in the direction. So it is trying to reduce this velocity. But if this bar is moving with a constant velocity, then you have to apply some force in this direction to keep it moving. So this is force applied, that is F subscript A. So if these two forces are equal, only then the bar will continue moving. So this force, this FB we denoted by ILB, and you know the current I is BL V by R from previous slides. So you multiply this current with LB and you get B square L square V by R as the force. Now what is the power? So the power, you know, is force times velocity. So power becomes B square L square V square by R. So B square L square V square by R is the power. And this you can see is immediately equal to this EMF over R. So in the previous lecture we computed this EMF as BLV. So this should remind you of the formula that power is equal to V square by R. On here we are replacing V by this EMF.